So this video will review transformations, single ones, and then in class we'll put them together and put more of a pre-calculus spin on them. So first let's talk about vertical transformations. There are three. You've got your vertical translation, or a shift up and down, your vertical reflection, or a flip, and your vertical dilation, where you go up more quickly or more slowly. We'll take them one at a time. But remember, vertical transformations show up outside the action. So if you're looking at an equation of the function, anything that's happening kind of after the action of the function is going to be some kind of vertical transformation. So vertical translation, first of all, happens when you are adding k after your function. So that's a vertical translation of k units. You don't need to be familiar with the function rule version, but you need to recognize it when you see it. So for example, here you have absolute value of x minus 5. You've got a minus 5 tacked on after the parent function. Now, if I were to rewrite it so it looked more like this, I would have a plus -5. That might be helpful to you. It might not. So this is a function that's being translated -5 units vertically. Now, we're going to look at this kind of point by point and look at some pre-calculus tips that we can put into place here. If you're trying to find points on your new function, you just have to kind of mess with the y coordinates if you're thinking about vertical transformations. So for a vertical translation, you just have to add k to the y coordinate of each point. I'll show you. So I'm going to pick a random point on my parent function, the red function. So how about here? So that's 3, 3. So I know I have a vertical translation of -5. My k here is -5. So I'm just going to take that original point. I'm going to add -5 to just the y coordinate to tell me that my new function has a point at 3, -2. And sure enough, if I look over here, I do have a point there. Vertical reflection. That happens when you have a negative outside your function. For example, the classic y equals -x squared, because you're squaring x and then you're applying a negative. So to get your new points here, you just get to multiply each y coordinate by -1. So for example, I had the point 3, 9. And so that's going to become 3, -9. And sure enough, I've got that point on my function right here. Vertical dilation. These are harder, I think, to see visually. So this is where I think that dealing with the points can be really helpful. So this happens when you have some number a multiplying your parent function. For example, y equals 3 radical x. So this, generally speaking, is a vertical dilation by a factor of a. And in this specific example, it's a vertical dilation by a factor of 3. My parent function is this black one here. That's radical x. And then my new one is 3 radical x. To get your new points, just take some points on your parent function and multiply their y coordinates by a. For example, on our parent function, we had the point 4, 2. So all I have to do is multiply the y coordinate by a, which in this case is 3. So I'm doing this times 3, which gives me a new point at 4, 6. And sure enough, I've got a point right there on that function. So, and I could do that with a few points just to give me an idea of how quickly and how steeply this function is going up. We also, of course, have horizontal transformations. As you might guess, they act on the x coordinate. You've got a horizontal translation, horizontal reflections, and horizontal dilations. So horizontal transformations show up inside the action before you perform the action of the parent function. So horizontal translation, formally speaking, looks like this. F of x minus h. That minus h is happening inside the function. And that's a horizontal translation of h units. Specifically, remember, you have to pay attention to a minus sign here. What I mean is this. So in here, my red function is y equals absolute value of x minus 3. I know that's a minus, and I know that means this is a horizontal translation of 3 units. 3 units to the right. So if I'm trying to go point by point here, I just have to add that k, that 3, to the x coordinate of each point. So for example, if I have the point, let's take that 3, 3 again. All I have to do is add my k, which is 3, to my x coordinate to say that I have a new point now at 6, 3. And sure enough, there it is. Horizontal reflection happens when you apply a negative inside the function. So for example here, again, that black function is radical x, and the blue one is radical negative x, because that negative is happening before I take the square root. So this is a horizontal reflection. To obtain it, you can just multiply each x coordinate by -1. So let's see if I had the point again 2, 4. I just have to make that x coordinate become -2, 4, and that's a point on my new function. And finally, the horizontal dilations. These can be a little weird, so pay attention here. So this is when you're multiplying x by some factor b before the action of the function, and it's going to be a horizontal dilation by a factor of 1 over b. So it's sort of opposite, kind of in the same way that the horizontal translations are opposite. So here, my black function is, whoops, I'm not starting this again. So the black function here is y equals x squared, and the green function is going to be y equals parentheses 3x all squared. So the 3 is happening before the squaring. So this is a horizontal dilation by a factor of 1/3. Just like with the vertical dilations, we just need to do some multiplying, but we're going to do it with the x coordinate. So we're going to multiply our x coordinates by 1 over b. So let's say that I have the point here. It looks like I've got one at 3, 9. So I don't know why I keep getting out of there. So I've got one at 3, 9. And then I'm going to take that point. I'm just going to multiply my x coordinates by 1/3. And so that gives me the point 1, 9. So I know I should have the point 1, 9 on my new function. And I could do that with a few different points to get an idea of what that parabola is going to look like.